In this video, we're going to look at the physical properties and basicity associated with amines and various other nitrogen-containing functional groups. Okay, and let's look at amines. Amines are derivatives of this compound, ammonia, NH3. Okay, as we add, and amines are just compounds where we've taken one of the hydrogens in ammonia and replaced it with R groups. Depending on how many R groups have been replaced, that determines our amine classification. So if one R group has been replaced, it's a primary amine. If we have two R groups at nitrogen, it's secondary. 3 R groups is tertiary. And we can even get a 4th R group on nitrogen. And this would be a quaternary ammonium salt. Okay, it'll have to have a positive charge now because there are 4 bonds to nitrogen. Okay, the hydrogen bonding issues associated with amines kind of depend on whether you actually have a hydrogen at nitrogen or not. So primary and secondary amines have hydrogens at nitrogens, and these can function as hydrogen bond donors and acceptors. Whereas tertiary amines do not have a hydrogen at nitrogen, but they still have a lone pair at nitrogen, which can accept a hydrogen bond. Okay, so they're hydrogen bond acceptors, but not hydrogen bond donors. Okay, we see this hydrogen bonding issues reflected in the boiling points of various amines. So I have on the second row here 3 different 6-carbon amines, and what we see here is that hexylamine, or 1-aminohexane, has a higher boiling point than the other 2. This is because it has 2 hydrogens at nitrogen. It can have a higher degree of hydrogen bonding, and you see the boiling point here is 132. N-heptane, this is a compound without any sort of strong intermolecular attractions. The boiling point is about 100 degrees C. So we see a boiling point that's significantly higher than heptane, and that can be attributed to the hydrogen bonding. Okay. This last compound, triethylamine, it can't have hydrogen bonding with other molecules of itself. It's also branched, and it has a much lower boiling point at 89 degrees. Okay, we see that the water solubility, however, is not really affected, and this is because all of these have the potential to function as hydrogen bond acceptors. So when dissolved in water, any of these can hydrogen bond with water through the lone pair. Okay. All right. So we see that all of these have some appreciable water solubility. All right. So I really, in this bottom structure, should have drawn a nitrogen here, but you really can't do that in my drawing program and still have the nitrogen be visible. Okay. But recognize that here we have an amine that has 3 different R groups on it. And there is no plane of symmetry here, so this looks to be a chiral compound, right? Well, it turns out that amines can undergo very rapidly a process known as Walden inversion, okay, which is kind of like an umbrella being caught in the wind. Okay, and this occurs at room temperature and above. So what happens here is that when an amine, which I've drawn as chiral, undergoes the Walden inversion, it produces its enantiomer, right? If we drop this down here, you would see that this was a perfect mirror image of that. So since it interconverts with its enantiomer, we can't really make a chiral secondary or tertiary amine. Okay, there are other functional groups, sulfoxides come to mind, that actually can have a chiral lone pair, okay, or have chirality involving a lone pair, but not amines, okay. All right, let's look at some other amine types, okay. If we just assume that all the R groups here are alkyl groups, these are just alkylamines. Let's see, let's just look at the 3 compounds where we have R groups defined. These are alkylamines. Okay. Arylamines have a benzene ring directly attached to nitrogen. Amines we've seen before. These are the condensation products of ketones or aldehydes plus primary amines. And here are some important heterocyclic rings that we're going to revisit. They have interesting aromaticity issues. This is pyridine. This is pyrrole. This is imidazole, indole, and pyrazole. Okay, let's look at one of the most important properties of amines, and this is basicity. Okay, so when an amine reacts with water, an equilibrium occurs to generate an ammonium salt and hydroxide ion. This reaction, for the most part, in most cases, will go very strongly to the left. This is because if we look at water, it has a pKa of about 16, and the amine has a pKa, ammonium salt has a pKa, we'll say around 10. Okay, so this is the weak acid. Okay. All right. Now, I have this equation going to the left. When you see this question asked on an exam, you're going to have to think of this a little bit more deeply, because the type of water being added here makes a big difference. The water I'm using in this equation here at the top is just plain old distilled water. In biological systems, the water is that floats around in blood and cells and things like that is rigorously buffered to a pH of just slightly above 7. So that water is different. So you'll likely hear somebody in biochemistry or biology argue with this point here, but again, it has to do with the type of water that you use. Okay, so you'll often see ammonia dissolved in water, and you'll often see it called ammonium hydroxide. That's a compound, or a label like this. This is mislabeled. Okay, it's not ammonium hydroxide. It's ammonia dissolved in water. Okay, ammonium hydroxide wouldn't smell like NH3. It would be volatile. Okay, all right. So again, this is an issue that kind of requires that you think about the type of water that's being used when it matters as to what is going to be the correct answer for this equation. All right, so we measured acid by pKa. What about pKb? Well, we can use this. This is the equation here for Kb. Okay, if you look at the equation at the top, the Kb is the concentration of the products over the concentration of the reactants. Water is being factored out because in dilute solution its concentration is relatively constant. And the relationship between pKb and the pK of the ammonium salt is very simple. It's governed by this equation here. Okay, the deal is that nobody uses pKb anymore. When people talk about amine basicity, they talk about pKs of ammonium salts. Okay, and you may say, well, isn't that stupid because amines are bases? Well, it is kind of, but I don't want to get into any philosophical arguments here. But pKa is universally used to express amine basicity. You just have to remember that when we talk about pKa of amines, we're often talking about the pKa of the ammonium salt. Okay, a big problem is that in people's jargon, they forgot this ammonium salt business, and oftentimes they'll say that pKa is something, and they're referring to its ammonium salt. So let's look at the simplest amine of them all, ammonia. Ammonia's ammonium salt is ammonium chloride, and ammonium chloride has a pKa of 9.3. Okay, so a lot of times you'll hear people say ammonia has a pKa of 9.3. You should correct them. Say, excuse me, do you mean the ammonium salt? And that would be the correct term. Okay, acetic acid has a pKa of 4.7. So a type of compound that we're going to look at later in this class is called alpha amino acids. Okay, so one way to write it is as a neutral compound here. But this reaction that we see here is actually going to go to the right, right? Because here is our strong acid, and here is our weak acid. And neutralization reactions, acid-base reactions, go in the direction of neutralization. So the zwitterion form of the amino acid is the most important form. Okay, now ammonia does have a pKa. Just like to remind you, ammonia has a pKa of about 34. And this is for reacting with base to produce NH2 minus. This is an issue we covered way back a long time ago with the alkyne chapter. Okay, and so we're not really going to talk very much about those types of bases in this chapter. All right, so let's look at some substituent effects on amine basicity. Alkyl groups are electron donating groups, and it's a lone pair that's making it basic. So it might say, okay, adding electron density to a lone pair, that's going to make the lone pair more reactive, and that is in fact the case. Alkyl groups increase the basicity. Okay, so if we go from ammonia to methylamine, the pK rises to 10.6. It rises all the way up to 10.7 by adding another methyl group. Okay, here's the problem. Okay, so let's take a tertiary amine and protonate it. All right, so this is actually kind of a sterically congested compound. So for that reason, it's resisting the attempt to put a fourth group at nitrogen when you have a tertiary amine. So that's why this effect is not necessarily additive. Okay, yeah, one alkyl group definitely increases the basicity, but 2 or 3, the effect is not 100% clear. Okay, so we have the steric effect that's working against the electron donating effect. Arylamines, like aniline here, are generally less basic than alkylamines like methylamine. Okay, so aniline, okay, remember the pKa's here are the pKa's for the ammonium salts, has a pK of 4.6. Therefore, aniline is a much weaker base than methylamine. And the reason it's a weaker base is because the lone pair is already engaged in some other activity. It's engaged in a resonance interaction with the benzene ring. Okay, so we can delocalize the basic site over the ortho and para positions by writing the two resonance forms that we see here, right? Okay, this one here is still the most important one because it's the only one that's aromatic, but these are contributing to the overall structure to some extent. So this is serving to reduce the basicity. Two aryl groups gives you an even less basic amine at pK of the ammonium salt from diphenylamine is 0.8. It's actually a fairly strong acid. Okay, electron withdrawing groups decrease the basicity, and electron donating groups increase the basicity. So we have a nitro group here. This is pulling the electron density away, so it's stabilizing the lone pair, and this is leading to an increase in the basicity. Okay, nitrogen at sp2 carbon is generally less basic than nitrogen at sp3 carbon. We see this with pyridine. Okay. All right, and finally, amides and amines where the nitrogen is part of the aromatic system typically don't have any basicity at all. Let's just do a little review here. Okay, so pyridine okay, that nitrogen, or the basic nitrogen, is orthogonal to the aromatic system. And in pyrrole, we actually need the nitrogen lone pair to get 6 pi electrons, right? Okay, so pyrrole would not be aromatic unless we include the nitrogen lone pair. So then, since that lone pair is needed for the aromaticity, that ends up not being a basic lone pair at all. The other compound I'll mention here, I didn't put it in the PowerPoint, but it's worth mentioning. The nitrogen of a nitrile is also not basic. Okay, let's do a little problem here. Rank the following compounds in terms of their anticipated basicity. Rank the most basic as number 1 and the least basic as number 6. This is a classic type of question you almost always see when you're talking about amines. Okay, so let's think about how we answer this. All right, so this is actually an amide base, and it's unfortunately that we call it that, but because this is an amide. So let's just remember that the amide nitrogen here, this nitrogen here, is not basic, whereas this nitrogen here is very basic. It actually has an anion. It's anionic. Okay, all right, so let's look at this. This is dialkylamine. This has an alkyl and aryl. This has 2 aryls plus an electron withdrawing group, and this just has 2 aryl groups. Okay? All right, so the negatively charged one is going to be number 1, and the amide is going to be number 6. The alkylamine is going to be more basic than any of the arylamines, so we're going to put the third one as number 2, and the next one is number 3, and we're going to rank the double aryl system that does not have an electron withdrawing group higher than the one that has an electron withdrawing group. So here is our ranking order that you see here. Okay, and again, I've explained it previously, but the electron withdrawing group is going to make number 5 less basic than number 4. The fact that you have 2 alkyls is going to make this greater than this. This is a very strong base derived from protonating a neutral amine, and this is nitrogen here is not basic. Okay, let's look at another classical question. Which nitrogen atom in N-methyl imidazole is more basic, and why? All right, so we have 2 nitrogen lone pairs here. And so we're wondering which of them would be more easily protonated. The way to do this here is really just to go ahead and protonate them and look at the 2 structures and see if there's something you like better about one structure versus the other one. All right. So if we do that, we find that if we protonate this top nitrogen, we get this compound. And what happened to our aromaticity? It's gone. We've put an sp3 atom into the chain. Okay, so this totally interrupts the aromaticity, and that's not as good a structure as the one below it, which is still an aromatic compound. Okay, so this nitrogen here, the one that I've shown in blue, is like a pyridine nitrogen. Okay, the nitrogen is part of a double bond, therefore its lone pair is outside of the aromatic system, whereas the nitrogen at the top is like a pyrrole nitrogen, and the lone pair is needed to make the system aromatic. So you don't want to get rid of that lone pair. It would cause problems with the stability of the molecule. Okay, and I think this may be okay. We have one more here, and this is solubility issues related to acidity. And I'm going to sort of clear up this question about what type of water do you have when you dissolve your amine in water. All right, so this is the Henderson-Hasselbalch equation. An important thing to remember here is that when the concentration of the anion and the protonated form become equal, the logarithm of this term becomes 0, and that means that the pKa and the pH are the same. So when the pKa and the pH are the same, you get an equal concentration of it. Let me just redo the Henderson-Hasselbalch equation here to reflect amines. Okay, this is because the amine is neutral and the protonated form okay, so let's just adjust it that way for amines. Okay, amine and protonated amine. All right, so ethylamine has a pK of 10.6, or ethylammonium salt has a pK of 10.6. This means if we take diethylamine and dissolve it in water, that diethylamine will only be the dominant species if the pK is higher than 10.6, whereas the ammonium salt will be the dominant species if the pKa is less than 10.6. Okay, this ionic ammonium salt is far more water soluble than the neutral amine. Okay, so what does this mean? Well, in biological systems, because they're rigorously buffered to pHs around just slightly above 7, this means that at biological pH, the ammonium salt is going to be the major form. And it's going to have quite a lot of solubility, okay? All right, but when you dissolve an amine in just plain old water, what happens here is that you actually affect the pH of the water. The water gets more basic as you add amine, okay? So when you take neutral water, pH 7, and you add an amine to it, the pH isn't 7 anymore. It's rising. So if we want to make an amine dissolve in water, we have to add some acid or something like that. Okay, let's look at a special use of something called phase transfer catalysts that take advantage of the fact that ammonium salt is more water soluble. Right, so here's a reaction we looked at a long time ago in chapter 14. This is carbene addition to an alkene. All right, so if you take chloroform and base, you make the dichlorocyclopropane. But if you really think about this reaction, what's the ideal solvent? It seems to be a difficult one, right? Because you have to have a solvent that's going to dissolve KOH, an ionic compound, chloroform, a polar organic compound, and cyclohexene, a nonpolar organic compound. So is such a solvent really out there that can dissolve all of these? Well, the way this reaction is often run is in a biphasic condition where you take water and dichloromethane. These don't mix. Dichloromethane's heavier, it's on the bottom, water's on the top. But if you add this compound here, benzyl triethylammonium chloride, which is a phase transfer catalyst, let's see, phase transfer catalyst. What it does is it exchanges with the KOH, okay? So you get our original KOH exchanging to make potassium chloride and this hydroxide, or tetraalkylammonium hydroxide, is actually soluble in both solvents. So you see that now the hydroxide will go into the organic layer, and this allows you to do this reaction quite efficiently. Okay, so this is a common use for ammonium salts in chemistry. Okay, so I'm going to stop this video here, and we're going to next look at synthesis of amines, then reactions of amines. Okay.